Okay, in this example we're going to apply implicit differentiation. We're asked to find the equation of the tangent line to the curve x squared plus y squared all squared is equal to x take y all squared. Now we're going to require implicit differentiation because this function is in implicit form. Notice it has y's distributed through the function expression. Now also keep in mind that y is a function of x. So every time we come across a y, we're going to have to apply the chain rule, and each time we do that we're going to produce a dy on dx. So at every y term that we differentiate we need to make sure we have a dy on dx term. Secondly, we need to keep in mind that as we differentiate this function we need to apply the differentiation rules that we come across. For example, x squared plus y squared all squared is a function of a function. It's this function squared. So we're going to have to apply the chain rule to this. Similarly on this one here, x minus y all squared is also a function of a function, and we need to be able to apply the chain rule to that. Now we're going to find the derivative because remember, to find the equation of a line, which is what the tangent line is, we're going to need to know the slope, and the slope is in fact dy on dx, and then we're going to need to use the point slope form, right, to find the equation of the tangent line. Alright, so let's begin. We're first of all going to have to apply the chain rule here. So we're going to have x squared plus y squared, and we take one off. This is the power rule. Alright, and then we're going to have to find the derivative of the inside function, which will be 2x plus 2y, and now we apply the derivative to y, which of course produces a dy on dx. Okay, so that's our left side. Now on the right side we have to do the same thing. We're going to have x take y, and of course we'll have a 2 in front, and then we'll have the derivative of the inside function, which is 1 minus dy on dx. Alright, so notice we have a 2 here, and over here we have a 2 as well, because we brought down the 2. Alright, the power rule, 2 by this function, x squared plus y squared, by the derivative of the inside function is equal to, bring the 2 down, power rule, x minus y, and then the derivative of the inside function, which is 1 minus dy on dx. Now of course, therefore, clearly we can cancel by 2. We're going to now apply the FOIL method to expand out the parentheses so that we can start to collect together the dy on dx's on the left side and everything else on the right side. So foiling this, we end up with 2x cubed. We're going to have here next we're going to have plus 2x squared y dy on dx. We're going to have a 2xy squared, and finally a 2y cubed dy on dx. Okay, so that's our left side. Now this will be equal to the right side, which is going to be equal to x minus x dy on dx minus y plus y dy on dx. Okay. Alright, now we need to now get all of the dy on dx's on one side, so we're going to have dy on dx over here. We're going to have a 2x squared y plus a 2y cubed, okay, from the left side. Now if you look on the right side, we're going to bring the x across, so this will become a plus x, and we're going to bring the y across, so negative y, and so this will be our left side with dy on dx as the common factor. Now this will be equal to, okay, we have to get everything else onto the right side. So if you look at the right side to start with, we have x and we have subtract a y. Right, now we're going to need to move this 2x cubed, so we get a negative 2x cubed. We're going to have to move this 2xy squared, so we're going to have a negative 2xy squared. Alright, so there's our right side. Right, now to put this together, what we're going to need to do is take this factor and divide both sides by this factor so we can get dy and dx by itself. So, to do that, we'll have dy on dx is going to be equal to, alright, so the right side, we can use that as the numerator. And so we end up with, right, x minus y minus 2x cubed minus 2xy squared as the numerator. And the denominator will be this here, which will be 2x squared y plus 2y cubed plus x minus y. Right, so this now is our expression for dy and dx, which is the derivative of the function in terms of x and y, which will be the slope of the function at any point xy. Now, of course, we have a particular point, so let's work on a particular point, and let's do that. Now, at the point, so we want to now do this, and we want to evaluate it at 1, negative 1. Alright, so notice here, wherever x is, we're going to put a 1, and wherever y is, we're going to put a negative 1. So we end up with a 1 subtract a negative 1 minus 2 by a 1 cubed minus 2 by a 1 by a negative 1 squared. Okay, all over 2 by 1 squared by negative 1 plus 2 by negative 1 cubed, and we're going to have plus 1 by plus a negative, or rather subtract a negative 1. Alright, so let's do that. We're going to have this is equal to then 1 plus 1 subtract 2, and here we have 1, so we're going to have subtract 2 again. Alright, let's be careful of this one. We have 2 by this, so it'll be negative 2. This will still be a negative 2 because negative 1 cubed is negative. We have a plus 1, and now we have a subtract 1, so it's going to be plus 2. So we end up with, alright, this goes with this, so I'll get a negative 2 on the top, and on the bottom we're going to have a negative 2, so I end up with 1. So the slope of the tangent is going to be 1. Right, now to work out the equation of the tangent, we use the point slope form. Okay, so this is our m. Okay, and our x1 and y1, of course, is 1, negative 1. And of course the x is 1 and y1 is negative 1. So this now becomes y subtract negative 1 equals 1 by x subtract 1. And this will become y plus 1 equals x minus 1. And so my equation will become y is equal to x minus 2, and this will be the equation of the tangent line at the point 1, negative 1 for this function.